Welcome back, everybody. In this video, we'll be continuing with section 3.4 by looking at how you can make up the formula for a polynomial function given some of the information about the polynomial. So we're going to try number 59 here. It says we want the polynomial to have degree 5. It'll have roots of multiplicity 2 at x equal 3 and x equal 1. So each of those will occur twice. And then a root of multiplicity 1 at x equal -3. And then it says something about the y-intercept, but we'll deal with that later. So for now, let's try to figure out what the factored form will start to look like. I know that x equal 3 will have to be multiplicity 2. So the factor x minus 3 will have to occur twice. And then x equal 1 is a 0. So we'll have x minus 1 as a factor, but it has multiplicity 2, so it will have to occur twice. And then x equal -3, that's a 0, so x plus 3 will be a factor. It occurs with multiplicity 1. All right, so this is going to be my kind of starting point. We'll call that capital F of x. This function has all the correct zeros and the correct multiplicities, but it may not have the correct y-intercept, but we'll fix that later. Meantime, what I would like to do is go ahead and multiply this out because we should be able to give our answer either in the factored form or multiply it out. So we're going to multiply this one out. It'll be a little time consuming, but we can do it. So first, x minus 3 squared will be x squared minus 6x plus 9. There I used the perfect square trinomial formula to get that done. X minus 1 squared will be x squared minus 2x plus 1. And then finally, I still have that factor of x plus 3. Okay, so now what to do next is I'm going to multiply the two. There's two multiplications to do here, right? There's two trinomials and one binomial that need multiplying. I'm going to just work from left to right, get this done. I'm going to multiply the two trinomials together. When you're doing polynomial multiplication, you need to make sure that every term in each polynomial gets multiplied. One of the ways of organizing that work is by using what is called a box method. So I'm going to make a rectangle and divide it into 3 rows and 3 columns. And then along the margins of the table, I'll put the terms for each polynomial. We'll have x squared minus 6x and 9 along one side, and x squared minus 2x and 1 along the other. So then what we'll do is to create the body of the table, we're going to multiply each row and column together. X squared times x squared will give us x to the 4th power. X squared times minus 6x is negative 6x cubed. Then we'll have 9x squared. Okay, continuing onward, we'll have negative 2x cubes, 12x squareds, and negative 18x's. And luckily for the last row, we're just multiplying by 1. Multiplying by 1 is always nice. Okay, so then what we're going to do is add up all of these terms. So this will be x to the 4th power. And then we'll have negative 8x cubes. And then 22x squareds. And then negative 24x's. And then finally the plus 9. All right, so that's the part where we multiply the two trinomials together. We still have to multiply by that x plus 3. Okay, so we used what's called a box method to get that first multiplication done. I'm going to do a different way of organizing the work just for variety's sake, show you another way to do this. For the next part, I need to multiply this x to the 4th power, big long thing, by x plus 3. So a second way of organizing the work is just to stack it. That is the two polynomials, one on top of each other. Kind of like when you're multiplying numbers together, like if you had 343 times 87, you'd write them on top of each other and, 7 times 3 and all of that. We're going to do the same sort of thing right here to multiply the polynomials together. So what we'll do is we'll do 9 times all this stuff first, and then we'll go back through and do x times all of the top terms, and then we'll add everything up. So we're working right to left. So we have 9 times 3 is 27. 3 times negative 24 will be negative 72. So we'll have negative 72 x's. 3 times 22x squared will be 66x squareds. 3 times negative 8, that will be negative 24x cubes. And then 3 times x to the 4th power is 3x to the 4th power. Okay, take a little break. Now we need x times all that stuff. When I go to multiply all these together, you'll see that I'm going to align the terms according to like terms. So when I do x times 9, it's not going to be all the way to the right. We'll have it under the prior x term. So x times 9 is 9x. Then we'll have negative 24x squared. And then 22x cubed. And then negative 8x to the 4th power. And then x to the 5th power. Okay, last step, and then we're done with this, okay? So we're going to add these two together. Luckily with this, there's no carries. So if you want, you can just work left to right. We'll have x to the 5th power, then negative 5x to the 4th power, negative 2x cubed, and then 22x squared, negative 63x's, and a 27. All right, so that's how that looks multiplied out. That's everything. But the thing is, so this was our big f of x, okay? And so we've fulfilled the requirements of having the correct zeros. The only thing that's missing is the y-intercept, because right now, f of 0 is going to be 27. And in the problem, it's supposed to be, sorry, I don't want to make you dizzy. It's supposed to be 9, okay? So what we'll do to fix that is we're going to take our existing f and we're going to divide through by 3. That will turn that final 27 into a 9. So I'll make that my little f, which will be my final answer. We're going to divide by 3. Okay, so we'll have 1/3 x to the 5th power minus 5/3 x to the 4th power minus 2/3 x cubed plus 22/3 x squared minus 21x plus 9. Okay, so that finally will do it. That will give us the correct zeros with the correct multiplicities, and then additionally we'll make it so that the y-intercept is correct. So one other thing worth mentioning is that this last thing that we did of dividing through by 3, what that did is it squished the graph, right? We talked about multiplying graphs or multiplying functions by constants and how that would stretch or shrink a graph. This one, dividing through by 3, which is the same as multiplying by 1/3, that is going to squish the graph vertically, right? And so that's what moves that y-intercept down from that 27 I had in the first place down to 9, where it should be. But it's not going to affect the zeros, the x-intercepts, because multiplying 0 by 1/3 will still be 0. So the graph will still have the same x-intercepts it had before. Note that another possible try to fix this would have been to say, okay, well, if it's 27 and I want it to be 9, let me take away 18. Okay, I can't just do that. I can't just say, okay, let's just subtract 18 from this, because if you do that, then that will shift the graph downward, and that is going to change what the zeros are. All right, so that takes us to the end of that example. Let's go ahead and do one more example of that, because I recognize that that can appear kind of tricky. So we're going to try also number 58. So in 58, it says we want a polynomial of degree 3. It's supposed to have zeros at -5, -2, and 1. So it doesn't say anything about the multiplicity there. So they're all 1. Plus, if it's degree 3, each one can only be multiplicity 1. So a kind of rough draft of this polynomial would look like x plus 5, x plus 2, x minus 1. Okay, that would give us all of the correct zeros. And let me check about the y-intercept. F of 0 will give us 5 times 2 times -1, right? And that's -10, right? Okay, so right now the y-intercept is -10. We need the y-intercept to be at +6. So we need to ask ourselves, okay, what should I multiply -10 by to be +6? And so that's a little equation for you to solve. You're going to end up getting -3/5. Okay, so we're going to multiply by -3/5 for our polynomial. That will create our new f of x, -3/5 times x plus 5, x plus 2, and x minus 1. All right, so that's how that'll look. I'll leave it to you to do the multiplying out if you want to see that. Okay, let me know if you have any questions on that. All right, so our next topic in this section is on something called the intermediate value theorem. The intermediate value theorem is something that's studied in more depth in calculus, but we will use kind of a simplified version of it here. It says this: suppose that f is a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, that is, one's positive and one's negative, then there exists at least one value c between a and b for which f of c is equal to 0. That implies that there's a solution of that equation, basically. So first thing to do is just a picture is going to make this clearer what this is actually saying. So first of all, f is a polynomial function. What that means, we know that the graph is smooth. It doesn't have any corners or any kind of jumps or infinite discontinuities or anything of that nature, right? So it's just a nice smooth curve that you could draw without lifting your pencil. Okay, so it says that if f of a and f of b have opposite signs, okay, so let me draw a situation like that. So here's a and here's b. So f of a could be positive and f of b could be negative. Okay, there's a situation where they have opposite signs. So let's say that you want to try to draw the graph of f, knowing that it's a polynomial. If you know that the graph is a polynomial and you're going to connect the dots, okay, it's a polynomial, so there's no jumps, gaps, or breaks or anything. If you connect the dots, are you going to have to cross the x-axis someplace? Yes, that someplace is a number c. Okay, you may have to cross more than once, or it may cross, you know, a couple of times, but eventually it will cross and get down here to that b. Of course, if the situation were reversed and our a was down here and our b was up here, okay, then again, if we're going to connect the dots between f of a and f of b, okay, well, it could wiggle a couple of times, but there is going to be at least one place where the graph crosses that x-axis. That's what the intermediate value theorem says. The version of this that appears in a calculus class, there's more relaxed. It isn't necessarily a polynomial function. It's any continuous function, and then there's a little bit more to it than that. But basically, the version of it that we learn in this class is just for polynomial functions. Okay, and we can use that to help us figure out that there's zeros of polynomials in certain intervals. So we're going to try that right here. So we'll do this for number 25. So here it says f of x is x cubed minus 9x. We want to establish that there is a 0 between 2 and 4. Okay, so let's just think for a second. I know that this thing is a polynomial, and so it's going to have a nice smooth graph. What is f of 2? F of 2 is 2 cubed minus 9 times 2. That's 8 minus 18, which is negative, 10, which is negative. And then f of 4 is going to be 4 cubed minus 9 times 4. That's going to be 64 minus 36. And that's going to be 28, which is positive. Okay, so what happened? F of 2 was negative, f of 4 was positive, so that means that the graph had to have crossed between over 0 in that interval. Somewhere between 2 and 4, the graph crossed, or the function crossed between negative and positive. So that establishes that there is in fact a 0 in that interval. It turns out for this particular function, it's not too hard to find it, right? If you factor x cubed minus 9x as x squared minus 9, you'll get x plus 3, x minus 3. So that 1, 0 that whose existence we showed was, we proved was the 3, right? 3 will be that 0. All right, so here's another function that might be more interesting. This is a function g of x, which is x cubed minus x plus 1. For this one, it's again a polynomial function, so we'll be able to apply the intermediate value theorem to this. So g of negative 1 is going to be negative 1 cubed minus negative 1 plus 1. That will be negative 1 plus 1 plus 1, which is 1, which is positive. So at negative 1, the function is positive. G of negative 2, that will be negative 2 cubed minus negative 2 plus 1. That will be negative 8 plus 2 plus 1, which is negative 5, which is negative. So g is negative at negative 2 and positive at negative 1. So there's a 0 or a solution of the equation x cubed minus x plus 1 equals 0 in the interval between negative 2 and negative 1. Okay, we don't know what it is, but it's in there according to the intermediate value theorem. All right, so that's the end of the intermediate value theorem. We just have one more example to do, and then we're finished with this section. So this one is kind of a story problem. We're just going to be creating a function subject to a couple of constraints. So here it says a square has sides of 12 units. So a square is 12 units long. We can say inches to make it concrete if we'd like. And then it says squares of size x plus 1 by x plus 1 are cut out of each corner, and then the sides are folded up to create an open box, or to express the volume of the box as a function in terms of x. So a good place to start with this is going to be with a picture. So let's see if we can draw the box first. Okay, so there's our square, and it has sides of length 12. And then we're going to be cutting out squares of length x plus 1 from each corner. So let's do that. Okay, so each square has length x plus 1. Okay, so then once those cuts are made, you end up with this shape that looks like kind of like a T or a cross. That's not a good picture. Let me make a better picture. Hang on a second. All right, that looks a little bit better. So what we're going to do then is take and fold up those sides to create a box with an open top, like the kind of box, bottom of a gift box you might get at the holidays or your birthday, or an In-N-Out Burger to-go box, right? Just an open top rectangular box. All right, so what we need to know is for the volume of a box, its volume is length times width times height. And so we need to know the length, width, and height of this finished box. So if the original dimensions were 12 and we're taking an x plus 1 out of each corner, then the width of the finished product will be 12 minus 2 x plus 1s. We're taking an x plus 1 out of each corner, and that's going to be true on both sides. We're taking 12, which is the length or width, and we're taking 2 x plus 1s from it. So that's 12 minus 2x minus 2, or 10 minus 2x. Okay, so that will be the width and length of the finished box. Okay, and then the depth of the box is going to be the size of the cut that we made, which is going to be x plus 1. Okay, so then the volume of our box, now as a function of x, is going to be x plus 1 times 10 minus 2x squared. All right, so there's our formula for our volume. So what would be fun to do next is take a look at the graph of the function. So let's see that. All right, so here's what the graph of our volume function looks like. So other thing to talk about is the domain for our v. Of course, we talked at the beginning of this section about how the domain for a polynomial was all real numbers. But the realistic situation here is that the x can't be any real number in the world, right? For one thing, x has to be at least -1, right? I didn't include that. X has to be at least -1 here because we have to have the cut size be at least 0. If you don't cut out something, then you just have a flat piece of square, cardboard or whatever. You don't have a box. So you have to cut out something. So x has to be at least -1 because x plus 1 has to be at least 0, right? And then additionally, x can't be any more than 5, right? Because the dimensions of our finished box, the width is 10 minus 2x. If x were bigger than 5, or even if it were 5, then we wouldn't have any kind of width or length. So the x has to be between -1 and 5. And so I drew this from 0 to 5. One thing that is interesting is that the maximum volume is going to end up occurring when when x is equal to 1, so that the cut size would be 2. All right, so that takes us finally to the end of this section. Let me know if you have any questions, and have a great day.